Good morning. It's a great Wednesday, isn't it? How are you all today? I'm doing pretty good today. It's not the greatest weather outside right now. It's a little cold and cloudy, but hey, you know, in just about a month or so, it's going to be really hot here. I mean, this Sacramento area goes from, you know, a winter with temperatures in, well, to use Fahrenheit, in the like 40s and 50s, which I guess would be, I'm kind of guess, probably like in the mid-teens, you know, in centigrade. And then by summer, we're rocketing up into the hundreds. And that's what, 38? Do I have my math right? Yeah. Up into the upper 30s, even the lower 40s. So it's nice to have a spring where it's just kind of like cool weather. Oh, I need to check something here. I'm a little concerned that we don't have anyone on Zoom right now. It's just me and you. Well, so what I was hoping to do was get a little interactivity today. Some people helping me out to solve some of these problems. So we'll see how we go with a fairly small audience right now. Oh, I guess we could wait another moment, see if anyone else comes. Who else is here? We got one person on YouTube. Two people. Say hello if you're there. All right, so I have a couple of, oh, here we go. Our Zoom folks are joining us. Good to see you. Hello, Lord Melbury from the UK. Good to see you back here. Well, let me put these problems up on the screen. Let me turn off the music. It's kind of distracting. There we go. So let me put these problems up on the screen. There's two problems to do, and I want you to take a few moments to see if you can solve them. At least try the first one. Post your answers in the chat, and then try the second one. So in the first problem, we've got a barrel with 100 balls in it. 20 of them are red, 28 are blue, and 31 are yellow. You reach into the barrel and you pull one of the balls out. What's the probability you pulled out a green ball? And then, if you subsequently pull out another ball, what's the probability you pulled out a blue ball? So given that you already pulled out a green ball, what's the probability of pulling out a blue ball? Okay, that's problem number one. And then problem number two is you have this diagram here where event Y is causing event X to happen. The probability of Y happening is 0.4. The probability of X happening, given that Y happened, is 0.1. And the probability of X happened, given that Y didn't happen, is 0.2. What's the probability that Y happens given that X happened? The question is, what are the colors of the balls? Yeah, there's only 4 colors of balls here. So we've got red, blue, yellow, and green balls, and that's it. Okay, so take a few moments to try to work those out. Good morning, Max, Spencer, and Serhi. Good to see you here.
Good morning. Good to see you too.
Yeah. Are you back in? You're the one that's in the science building usually, is that right?
I'm actually at home right now because my chem teacher is like interviewing today, so he canceled class.
Yeah, this is interview season. I had interviews, what was it, a week and a half ago. We were interviewing for a full-time computer science instructor. Unfortunately,
Did you guys end up making a hire?
no, we only got 7 people applied, which is a really low number. And then of the 7, we actually invited all 7 to come interview. But of the 7, only 3 actually signed up to interview with us, and then we couldn't find a suitable candidate out of the 3. So we'll search again in the fall. We'll put out the call again. If you're watching this, what we need as minimum qualifications is a master's degree in computer science. So we're looking for someone with a broad spectrum of knowledge across many different areas of computer science, including just introductory topics, along with things like Unix and Linux, C programming, Java programming, web programming, assembly language. So that, what I call a generalist. So if you're looking for a good full-time position, great, somewhat flexible hours, hey, apply with us. It'll be in the fall. Okay, if you're just joining us, we've got a couple of problems up on the screen here. First problem is you got a barrel with 100 balls in it, and 20 of them are red, 28 are blue, and 31 are yellow. You pull out a ball at random. What's the probability you pulled out a green ball? And there's only those 4 colors. And then the second problem, or part 2 of the first problem, is given that you just pulled out a green ball, what's the probability of pulling out a blue one? Okay. Let's do this. Let me just pause the music here. So let's go over this first problem. So in the first problem, we got 100 balls. Let's figure out how many green balls there are. So there's 100 minus 20 minus 28 minus 31. So there must be 21 green balls. So the probability of pulling out a green ball is 21 out of 100, or 0.21. So you reach into the barrel, there's 100 balls in there, you pulled out a green one with a 0.21 chance. What's the probability of pulling out a blue one given that you pulled out a green one? So after you've pulled out that green one, there's now 99 balls left in the barrel, and there is a 28 out of 99 chance of pulling out a blue one. Let's see, let me get out my calculator again. So 28 divided by 98 is 0. It's pretty close to 0.28, but it's a little bit less. Or a little bit more, 283, let's call it. So the thing to keep in mind out of this problem is that the number of balls is now reduced as you pull the balls out of the barrel. Actually, you're probably wondering what's behind my little picture here, if my picture is covering up the corner, and it's just a picture of the barrel. I'm sorry it covers it up a little bit. Okay, problem number 2. This looks like a job for Bayes' rule. So to compute the probability of y given x, that's equal to the probability of x given y times the probability of y over the probability of x. So let's look at this. We know this number, it's right here. And we know this number, it's right here. But we don't know this number. We don't know the probability of x, so we have to figure that out. And to figure that out, we need that decision tree. So event y comes first. You can see that from the diagram here. We've got y drawn going to x. So as we draw our decision tree out, we draw that in the same order. Y comes first, and then x. So one branch here is the probability of y, and one branch is the probability of not y. And we know what those numbers are. The probability of y is 0.4, so the probability of not y must be 0.6. Both of those have to add up to 1. I can see I'm going to need more space, so let me just move this over a little bit. Okay, and then 2 more branches off of this top x. And so this top branch here is the probability of x given y, and the bottom branch is the probability of not x given y. We know this number, it's 0.1, and the bottom number must be 0.9, because both of those need to add up to 1. And then finally we got 2 more branches down here. This is the probability of x given not y, and this is the probability of not x given not y. And those numbers are 0.2 and 0.8. So to compute the probability of x, we look at what paths do we have to take to go through this tree to get to x. And that would be this top branch, and then this zigzaggy branch over here. Both of those end up with x as the last variable in the sequence. Okay, probability of x given y is 0.1, probability of y is 0.4, and then the denominator here is going to be kind of large. We've got 0.4 times 0.1, that's this branch, plus 0.6 times 0.8, nope, not 0.8, 0.2, that is this other branch. Okay, 0.1 times 0.4 is 0.04, and the bottom is, again, I need my calculator for this. By the way, if you've never used one of these Hewlett-Packard calculators, let me see if I can get it to focus. There we go. If you've never used one of these Hewlett-Packard calculators, they're kind of unique because they're known for using what's called reverse Polish notation or postfix notation. So if I want to add 2 and 3 together, I don't type 2 plus 3. What I type is 2, let's see if you can see it appear, 2, and then I press enter, and then 2 gets pushed onto a stack. And then 3, enter. You can see those 2 numbers are now on the stack. and then I press plus, and it pops those two numbers off the stack and replaces it with the sum. So let's try that again. If I want to do, let's say, well, let's do the problem we've got here. We've got point. See, you probably can't see this because it's way too small. Here, let's make it bigger. So we got this problem. We're going to do 0.1 times 0.4. So I'm going to go 0.1, enter, 0.4, and then I actually don't have to hit enter. I can just hit times at this point. And you can see right here, I've got the result of multiplying 0.1 times 0.4. Now, what's the use of this, you say? Well, now this numerator is sitting on the stack. Now I'm going to calculate the denominator separately, and I'll be able to see the result of the denominator both on the screen at the same time. So that's going to be 0.4, enter, 0.1 times, okay, it comes out to be the same thing, and then 0.6, enter, and then 0.2 times. So there are the two terms from my denominator, and now I'm going to hit plus, and we'll add those two together. So now I can see the numerator and the denominator. So it's 0.4 on the top, and what is that? 0.16 on the bottom. And then I'm going to hit divide. And then I get my answer, which is what, 0.25. So let's switch back over to here. We got 0.16 and then 0.25. So I kind of like this style of calculator for doing more complex operations because you can see the intermediate results as you are doing the calculations, as opposed to your more traditional calculator. Let me see if I can get one of those out here. As opposed to something like this, where you're going to put in 0.1 times 0.4. Oh, we need that in parentheses, so let me go ahead and put parentheses around that. Which is around here. Parentheses there, and then parentheses there, right? And then we're going to go divide by, and then we'll open the parentheses and do 0.4 times 0.1 plus 0.6 times 0.2, close parentheses. So I've got my entire expression written out here across the top, but then I'm just going to press equals, you know, and I get the answer, 1/4, which I have to convert to decimal right here. I just press this S to D button right here. So I can see the point, there we go, 0.25, but I kind of have to take it on faith that, you know, this is the answer to the entire expression. I can't see the results of the intermediate calculations along the way. I mean, I could do it if I did the calculations separately and then use the answer button to make use of the previous results. But this style of calculator just gives you those results and shows it to you on the screen as you're doing it. So it's kind of nice. Also, your geek cred will go way up if you have a Hewlett-Packard calculator. Just letting you know. Oh, right. So on these Hewlett-Packard calculators, no need for parentheses. Not at all. I mean, this calculator does do infix notation, the kind you use on a regular calculator. You can switch it to that mode. And so it does have parentheses somewhere on the keyboard, but it's not one of the easily accessible keys because normally you use it in postfix notation or reverse Polish notation. Do your calculations that way. Okay, so the answer was 0.25. So here's another problem, another Bayes rule problem. So we've got this diagram, event A is causing event B to happen. Event A happens with a 0.37 probability. Event B happens with a event B, given that the event A happened, is 0.73. And then the probability that B didn't happen, given that A didn't happen, is 0.12. And we want to know what's the probability of A happening given that B didn't happen. So whenever you're doing these Bayes rule problems, I'm almost always going to give you 3 numbers, but there's a total of 6 numbers that you need. You know, in that decision tree, you can see that there's 6 numbers. So the thing to do would be to first calculate those other 3 numbers. I'm not going to draw the tree just yet. Let's just see if we can calculate those other 3 numbers without the tree. So on this top row, we've got the probability of A happening is 0.37. So the complement of that must be the probability of A not happening, and that's 0.63. So this row needs to add up to 1. And then this row also needs to add up 1. The complement to the probability of B given A is the probability of not B given A. So the only thing you do is you just invert the first variable. You leave the second one the same. And this is 0.27. And then finally the complement of not B given not A is B given not A. And that's 0.88. So each one of those rows needs to add up to 1. Okay, so to calculate this probability, we're probably going to need Bayes' rule. And one thing that I look for is the probability I'm trying to calculate in the opposite order of the numbers that I'm given. So I'm given probabilities of B given A. So the order goes BA, but I'm trying to calculate AB. And Bayes' rule is good for flipping the order of those events. So in the first factor of Bayes' rule, you take the variables and you flip their order. Then you multiply that by the probability of the variable in the second position, which is this one here. And then you divide by the probability of the first variable. So I take these two and I flop them around. And then the A goes over here, and the not B goes down here. That's how I remember how it all fits together. All right, so we have this number. It is right here. And we have this number. It is over here. We don't have this number. We don't have the probability of not B. So for that, we're going to need that tree. So in the tree, we've got the probability of A and the probability of not A. That's the first event that happens. And then on the right-hand side of the tree, we've got the probability of B given A and the probability of not B given A. And we have the probability of B given not A and the probability of not B given not A. So there's our 6 numbers. We need the probability of not B, which is right here and right here. So we need this path through the tree and this one. So let's just expand out the numerator and denominator of Bayes' rule, and then we'll plug in the numbers. So So we got probability of not B given A times the probability of A divided by this long denominator. Probability of A times the probability of not B given A. And that is this branch that I just highlighted, plus the probability of not A times the probability of not B given not A. And that is this bottom branch. So now that we've expanded that out, let's go ahead and plug in the numbers. 0.27 times 0.37. I got those two numbers out of here and here. And then in the denominator, I've got 0.37 times 0.27 plus the probability of not A is 0.63, and the probability of not B given not A is 0.12. Okay, and then here's where that calculator will come into play. So I'm going to go 0.27, enter, 0.37 times, there's my numerator, and then 0.37, enter, 0.27 times, there's the first term of my denominator, and then 0.63, enter, 0.12 times, there's the second term of the denominator, and then I'll do plus. So now I've got the numerator and the denominator right here on the screen, so I'm going to write those down. Zero 0.0999 divided by 0.1755 is equal to 0.0999 divided by 0.1755. This was a 6 right here. I'm trying to complete all my notes. This was a 6, I believe. Okay, and now I just hit divide. And there's the answer. So I have a 0.569. And Akash got that. Very good. 0.569. So one thing you've probably noticed in doing these problems is there's some patterns start emerging. One is you might have noticed that the numerator and part of the denominator would just work out to be the same value. You can see this one here, you can see the same thing over here, it's just in reverse order. And the other is that if the decision tree was larger, like there were maybe 3 stages to it, or as we saw last time, there was the 3 possible outcomes for that biopsy. You know, either it was normal, or you had lung cancer, or you had sarcoidosis, right? So that decision tree was still just 2 layers deep, but then there were 3 branches on that second layer. So the decision tree gets much more complicated, and so your denominator gets a whole lot longer. So now that you know how Bayes' rule is calculated, let's see how to calculate Bayes' rule, but using a technique of putting the numbers into a table, When you put them into a table, it still calculates the same values, but it's a better way of kind of like organizing the numbers so that we can run calculations that are longer without doing these huge giant denominators. Let me show you. So here's the exact same problem, but I'm going to show you how to use it using a table. First, let's calculate the other three numbers that we need. The probability of not A is 0.63. The probability of not B given A is 0.27. And the probability of B given not A is 0.88. So we already know we need at least a few of those numbers. So when you're doing Bayes' rule, each one of the terms or factors within Bayes' rule has a name. Here's Bayes' rule for our particular problem. And this factor right over here is called the prior, because it's the event that happened first. So when we lay out our table, I'm going to put in these columns. I'm going to put in a column for prior, not B, and then something called P prime, and then P. And then down the left-hand side, I'm going to put in the variable that corresponds to the prior. In this case, it's A, and I'm also going to need not A. Okay, so you look over here. What's the term that's all the way on the right-hand side of Bayes' rule? That's called the prior. So you're going to have a column labeled prior, and they're going to put in both variations on that variable. Either A happened or it didn't happen. And then this not B here comes from the other thing you're trying to calculate. This is not B given A. So given that the prior happened, what's the second variable in the chain of events? And so it's not B in this case. This P prime here is called your, I guess, your partial probability. It's not the full probability yet. It's an intermediate calculation. And then, whoops, this should not have a prime on it. This final column, which is just P, that's your final probability. So here's how we're going to calculate it. So in the table, we're going to put the probability of A under the prior column and the probability of not A at the bottom of the first column. In the second column, we're going to put the probability of not B given A. So that's a combination of this variable and this variable, or I should say this one and this one. And we're going to put in the probability of not B given not A, which is a combination of this one and this one. So you can kind of think of these as being intersections. Then you're going to multiply those together. And you're going to come up with a product in the top row. And you'll come up with a product in the bottom row. And then you're going to add those together and come up with a sum. And then you're going to divide that top number by the bottom number. And this is going to be your answer. This is the probability of probability of A given, whoops. What are we trying to calculate here? Probability of A given not B. Okay, so this number goes over here, and this number just goes straight across. Okay, so that's where the numbers go. Now let's actually put the numbers into the table. So let's draw the table again. I've got A and not A over on the side. I've got prior written here, not B, P prime, and then P. So my prior is the probability of A. We can pull that right off of my table of values, 0.37. And then down below, we've got the probability of not A, so that's just a complement of 0.37, 0.63. And then the probability of not B given A, again, comes from our chart here, which is, not B given A, 0.27, there it is. And the probability of not B given not A is 0.12. Multiply those. Get my trusty calculator here. 0.37, 0.27 multiply gives us 0.0999. And then 0.63 enter, 0.12 times gives us 0.0756. And then we're going to add those together. And I get 0.1755. And then finally in my P column, I bring over the 0.0999 and I divide it by 0.1755. So let's see, I need to put those numbers back in here. 0.0999. And then divide, and I get my 0.569. Okay, so we got the same answer, but now we've just laid it out in a table. And you might have noticed here that this number right here is, of course, the denominator from this page over here. And this number up in here was the numerator from this other page. So we ended up calculating the same values, just that we laid it out horizontally in a table. So I'm gonna go on a little tangent here for just a moment. So you probably noticed that I write out these events kind of like this, right? So we've got event A happens, and that causes event B to happen. And this is a very simple, like, conditional diagram. It shows that event B is conditional on event A happening. But the cool thing about Bayes' rule is that we can actually calculate the probability of A having happened in the past, given that B happened in the present. So that was like one of the big insights from, I guess, this mathematician named Bayes, who realized that you can calculate the probability of an event having happened in the past with current information about what's happening right now. So you don't know whether or not it happened in the past, but you can calculate that. And so that allows us now to draw like more complicated diagrams. Like, if it is cold outside, that causes me to want to put on a sweater, and it causes me to want to, let's say, have a nice hot bowl of soup. Okay, so this event here has happened in the past. It's cold outside, and so it causes me, or whether or not I want to wear a sweater is conditional upon the weather outside. And whether or not I want to drink some nice warm soup is also conditional on the weather outside. But with Bayes' rule, we can actually now calculate things like, if I am wearing a sweater today, what's the probability that it's cold outside? Or if you see me drinking soup, what's the probability that it's cold outside? Or even better than that, if you see me wearing a sweater, what's the probability that I'm also drinking some soup? Right? Or you can do stuff like if I get, let's say, a pay raise, or I'm eating a cookie, then that, like, you know, causes my happiness. Right? So if I get a pay raise, I'm happy, or if I'm eating a cookie, I'm also happy. Right? And so now again, with Bayes' rule, I can reverse those calculations. I could say, like, you know, if you see me being happy, what's the probability I just got a pay raise? Or what's the probability I'm eating a cookie? Or even better yet, if you see me eating a cookie, what's the probability I just got a pay raise? Right? So Bayes' rule allows you to really calculate the probabilities of really, really complex dependency diagrams, right? You know, you can have, you know, stuff like this, and all of these things, right, can be calculated just by applying Bayes' rule over and over and over again. So I think that's really cool about how all this stuff is possible now, given Bayes' rule, whereas these things were, you know, I don't remember when the Bayes' rule was invented, back in like the 1800s or 1700s. Back before then, it was just like a complete mystery. You know, no one really thought about how could you calculate the probability of something happening in the past, given what you know about the present conditions. Anyway, so last time we had these sort of made up numbers, like this cancer question, and you know, remember the setup was like, you know, you go to the doctor's office, you're not feeling too well. Doctor thinks like, well, we probably should run a test for cancer, and let's just see what happens. So the test comes back positive, right? We want to know, what's the probability you have cancer given the test coming back positive? Oh, that's what I already have written on the screen here. So to be able to calculate that number, we first derive the other three numbers. We're given 3. There's a total of 6 numbers. We just need to come up with the other 3. Probability of not cancer is 0.99. Probability of a negative test given cancer is 0.1. The probability of a positive test given not cancer is 0.2. So let's set up our table. We're going to do the exact same calculation we did last time, but using a table. We've got our prior column, which is C and not C. Then we have our positive test, P prime, and then P. So in the first column, we're going to put the probability of C, which is 0.01. And down below it, we're going to put the complement of that, 0.99. And then under the plus column, we're going to put the probability of a positive test given the prior, which is cancer, which is 0.9. And then below that, we'll put the probability of a positive test given not cancer, which is 0.2. Then multiply across. And again, calculator time. We have 0.01 and 0.9, which is 0.009. And then 0.99 and 0.2, which is 0.198. So now I'm going to add those together. 0.207. Now I get 0.009 divided by 0.207. And I get 0.0435. Let's call it 0.043. And so we came up with that number last time, and then I asked the question, what do you think about that? So you run this test, and it turns out there's about a 4% chance that you have this cancer. And you might say, whew, dodged a bullet there. There's not really that huge chance that you've got it. Or you might think, wow, that's like a 1 out of 25 chance. Let's be more cautious about that, and maybe let's run a test again. Let's run the same test again and just see how confident we are about that result. So let's calculate the probability of having cancer, given that we run the test twice and the test comes back positive both times. So what this diagram looks like is we've got the cause, the cancer, we can't see, the unobservable cause, and that influences the outcomes of these tests. Now, these tests are independent of each other. The outcome of one test does not influence the outcome of the other test. Doesn't matter what order you even do them in. So the outcome of the tests are conditional on the cancer, but the outcomes of the tests are not conditional on each other. So here's how we're going to set it up. We're still going to put in the prior, which is cancer, not cancer. Now we're going to put in 2 columns for the positive tests, and then our P prime and P. So under the prior column, it looks the same, 0.01 and 0.99. Under the plus column, it looks the same as the table above, 0.9 and 0.2. But then we have the same plus column again, and this is the intersection of the positive test and the cancer. So it's the same numbers. And then we're just going to multiply all the way across. And we're going to end up with, we're going to put it in here, 0.01, 0.9, 0.9, 0.0081, and then we got, let me do it again here. I got distracted for just a moment here. 0.99, 0.02, no, 0.2, and 0.2, and that's 0.0396. And then we're going to add those together and get 0.0477. Then 0.0081 divided by 0.04, need some more space here, divided by 0.0477 is 0.167. Okay, wow. What do you think about that result? Compare this number with the original one. So we ran the test twice, and we come up with a 0.16 probability of having this cancer. What is that? I mean, imagine this is you, right? You're in the hospital or doctor's office. They've run the same test twice. They both came up positive. Now, this by no means indicates there's a 100% chance you have the cancer. You have a 0.16 chance, but it went up by a factor of 4. So whereas you had a 4% chance before, now you have a 16% chance. So it's still nowhere near 100. Maybe what would you do now? Maybe run a third test? Maybe run a different test. Maybe there's a different test they can do that has a different probability of giving you a positive or negative result. Okay, so here's the same numbers. The probability of having the cancer given a positive test is about 4%. But let's say we have a different scenario that came up. We ran that first test, it came up positive, but we ran the test again, and this time it comes up negative. What's the probability we have the cancer now? So we'll set up the table, and I want you to take a moment to figure this one out. So I'm going to show you what the contents of the table are, or at least the labels on them. Try to figure out what is going to be the probability that we have the cancer given that we have two tests, one came out positive and one came out negative. So I would start by calculating the other three numbers, then start plugging those numbers in for these three columns, and then calculate the probabilities over here. So take a moment to plug those numbers in, run the calculations, and let's see what you get. Max says he got 0.01. Were there more significant digits to that? Like, carry it out a little bit further. Like maybe do 2 or 3 significant digits. Well, why don't we try working out this problem? Maybe I'll give you another minute. Just so the music ends right at the end of the song. Okay, so I started putting in the numbers. The probability of a negative test given cancer is 0.1, and the probability of a negative test given not cancer is 0.8. And we're going to multiply across. And calculator time. 0.01, 0.9, 0.1 times is 0.0009, and then 0.99, 0.2, 0.8 times is 0.1584, and we're going to add those together, 0.1593, and so 0.0009 divided by 0.1593 is 0.0056 565. So wow. So we had the one test came back with a 4% probability of having cancer. Ran the test again, got a positive result, and then it jumped up to a 16% chance. But with one of them coming back positive and the other one coming back negative, the probability fell way down to 0.5%. So it's almost like if you come back with two tests and one of them is negative, you might as well just say the probability of you having cancer is really, really small. So now that you've seen how to solve these Bayes rule problems using a table, let's see how to apply that to the original problem that I talked about last time, which was how do spam filters work. If you remember from last time, we started out back in the 90s with these huge lists of patterns to look for, specific phrases or specific words, sometimes specific words misspelled in specific ways, that would give us some kind of clue that this message we were trying to categorize was either spam or ham. And then Bayesian filtering comes along that's not only adaptable, it's able to learn from examples of spam and ham, it's also much faster at categorizing these messages. So first, a little bit of background here. A spam filter does not actually, or I should say a Bayesian spam filter, does not actually look at the order of the words in the message. It only looks at purely statistics about the message. It considers an email message. Here's a very simple one that has 5 words in it. Hello, I will say hello. It considers that to be just a set of words, no particular order, and in fact it removes all the duplicates. So the first thing it does is it analyzes that email message and then computes a dictionary where each one of the words has been listed just once in the dictionary, and then their frequency has been calculated. So hello appears twice, and I and will and say appear just once each. So the other thing to know about these spam filters is that they only know what they've been shown. So if this one email message is the only email message this particular spam filter has ever been shown, it calculates the statistics based upon just this one thing. So having been shown just one email message, it believes that all email messages follow these same statistics that I'm going to calculate here in just a moment. So what's the probability of the word hello appearing in another message? So remember, it's only been shown one email message in its entire life, and it's been composed of those 5 words. What's the probability that another email message that comes in is going to contain the word hello? Well, that would be 2 out of 5. Right? Hello appears twice, and there's a total of 5 words. What's the probability that a given word is the word will? It's 1 out of 5. And what's the probability that a given word is the word today? Right, that's 0. So even though we as humans know that today is a word and it gets written occasionally, the spam filter doesn't know that because it's only been shown this one email message, and it thinks that the only words basically that ever exist are hello, I, will, and say, and the word today does not exist at all. Okay, so let's expand this out a little bit. Here are, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8 email messages, and I'm keeping them short just for illustration purposes. So we've got one message here, one here, one here, and there's 5 more over here. So each one of these lines is one email message. And we've already gone through, as a human, we've already gone through and categorized 3 of the messages as being spam and 5 of them as being ham. So this is an important part of the training phase of a spam filter. It has to be shown a corpus of email messages, and those messages have been categorized, probably by a human, as to either being spam or ham, so that it can learn from that and compute statistics from those 2 categories of messages. So the first question is, how many messages are there altogether? And that's easy. There's 8. How many distinct words? So look at all the messages. How many distinct words? Remember, we're going to consider this to be a set of words, and we want to know just how big is that set. So you got to go through this and just count up all the words. So we're not looking for the total number of words. We want to know how many distinct words are there. This is more difficult to do for humans, right? Because your eyes just kind of like, they go crazy after a while. So Max, you said there's 13. I think I counted them and I got 12. So pretty close. Computers are much better at that problem. How many words are there total? How many words altogether? So just count up all the words, which was the total number of words. No, not 9. How many words total? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There's a total of 24 words. And maybe what you're thinking about is the next row down here, which is how many total words on the spam side. And that's 9. And how many total words on the ham side? That's 15. Okay, so this spam filter has been shown a total of 8 email messages. What's the probability that any given email message is spam? Good. 3 out of 8. And what's the probability that any given email message is ham? Five out of 8. Good. Given that a message is spam, so it's over here on the left-hand side, what's the probability that some word is the word secret? Okay, what's the probability that, given a message is spam, what's the probability that some word is the word secret? Okay, to figure this one out, we've got a total of 9 words in here from this number, and 3 of those 9 are the word secret. Remember, you would have built up a dictionary, and you would have shown that secret appears 3 times, and there's a total of 9 words. So this is 3 out of 9, which is 1 over 3. Given that a message is ham, what's the probability that some given word is the word secret? So now we're over here on the right-hand side. There's a total of 15 words. And secret appears once. So this is 1 out of 15. Okay, now, given that a word is the word sports, what's the probability that that message is spam? So let's say we've got an email message that came in. It consists of just one word, sports. What's the probability that that message is spam? Now to compute this, we're going to need Bayes' rule. So this is the probability of the word sports, given that the message is spam, times the probability of spam divided by the probability of sports. Okay, so the probability of a word being sports, given that the message is spam, which is over on this side, sports appears once. This is 1 over 9. The probability that a message is spam is 3 out of 8. And then we want to know what's the probability of just the word sports appearing. So there's a total of 24 words. And sports appears 1, 2, 3, 4, 5, 6. 6 times. And I need a little more space, so let me just squeeze these in a bit more. All right, so we have 1/9. I know there's a way to do fractions on this. I just have to remember what it is. I mean, I can do 1 divided by 9. I can do 1 enter 9 divided by. But there's a way to do fractions. There's so many words and symbols on each one of these letters. I don't remember how to do the fractions on here. I mean, I see the reciprocal. That one's easy. I'll just do 1 divided by 9. 1 enter 9 divided by. and then 3 enter 8 divided by, and then we'll multiply those together, and then we'll do 6 enter 24 divide, and then we'll just divide those, and we enter with 0.16666, which I believe is that 1/8? No, it's 1/6. 1/6. Okay, so you just need Bayes' rule to be able to calculate whether a message is spam or not. So let's do Bayes' rule again, but this time we'll use a table. So we'll set up our prior, and we have spam or not spam, which means, you know, it's ham, right? If it's not spam, it must be ham. Then we have secret, P prime, and P. Okay, so the probability that a message is spam is 3/8 or 0.375. And the probability that it's ham is the complement of that, 0.625. The probability that a word is secret, given that the message is spam, is a secret appears 1, 2, 3 times. So 0.333. And the probability that the word is secret, given that the message is ham, is secret appears once. So that's that's 1 out of 24. Let me see. 1/24 divided by, no, not 24, 15. 1 enter 15 divided by, there we go, 0.0667. Multiply across. So 0.375, 0.333 is 0.141248. And then 0.625 and 0.0667 multiply gets us 0.0417, and then we're going to add those together, and we get 0.1666, something like that. And so to calculate the final probability, we get 0.1248 divided by 0.1666. And that gives us let's just call it 0.75. So if an email message comes in and it just contains the word secret, or is the word secret, there's a 3/4 chance that it's spam. So that's for a one-word email message. What about for a longer message? What's the probability that a message is spam if that message is secret, right? It contains secret twice. So here's where the table really pays off. Got our prior column, which is spam, ham, our secret column, our is column, and secret column. our P prime, and our P. So I know what goes under the prior column, 0.375 and 0.625. I know what goes under the secret column, because I just computed that up here, 0.333 and 0.0667. And the same thing goes under the other secret column. But what goes under the is column? Can you figure that out? So what's the probability that a given word is the word is if the message is spam? So you look over here. And what's the probability that a word is the word is if the message is ham, which is over here? What two numbers go in that column? So take a moment to figure that out. Multiply across, add on the P prime column, and then compute the final probability. Oh good, Akash, you've got it. It's 1/9, which is 0.111, and 1/15, which is 0.0667. So now you're going to multiply straight across. Come up with the rest of the numbers. Okay, let's do these calculations. Oh, sorry, that was a sudden ending to the song. Okay, let's do this here. 0.375, enter. 0.333, enter. So when you have a whole bunch of numbers to multiply, you can actually just enter them all and then hit multiply a whole bunch of times to unroll that stack. 0.111, enter, and 0.333, enter. So I've got, whoops, that should be 0.333. There we go. So I've got all four of those numbers stacked up here. And then I'm just going to go multiply, multiply, multiply. The question is there a hidden assumption that all the words in the email are independent of each other? Yes, there is. The email spam filter just looks at an email message as being a set of words. So the order of the words doesn't matter. So all the words are independent of each other. Okay, so this is the number for the numerator. And because I know that this number is going to be needed again when I do that final division, I'm going to duplicate that number so it appears twice on the stack. Now I'm going to do the denominator. 0.625, enter. 0.0667, enter. 0.0667 again, enter. And again, 3 times, 0.0667, enter. So now I've got, come on, there we go. I've got those 4 numbers. Now I'm going to multiply, 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 multiply. So this is the denominator down here. Or I should say it's the second number. So let me go ahead and, oh, you probably can't even see what I'm doing. Here we go. All right, so now I've got all these numbers, and I'm going to put them over on the display. So I have here 0.00462. And I have, oh, this is a small number, 0.000185. Okay, focus, focus, focus. There we go. So now I'm going to add those together. Where's my add button? Right here, add. Okay, there's the sum. And then I will, oh, I guess I should write that down before I lose track of it. Zero point zero zero 480. Okay, and then one last calculation. I'm now going to divide these two. There's my final answer. Oh, that didn't work. There we go. So 0.00462 divided by 0.00480 gives me 0.961. Wow. So if the email message is secret, I've got a almost 100% chance, not quite 100%, 96% chance this message is spam. So one more example. What's the probability the message is spam if the message is today is secret? So let's set up the table. Got our prior, today is secret, P prime, and then P. We have over here spam and ham. So the prior is 0.375 and 0.625. We already know those numbers. But for today, today never appears over in the spam side. So that's a 0. And we can actually already see this is going to cause a problem. Because if I multiply these numbers across, I'm just going to get 0 here. And then if I multiply these numbers across, I'm going to get something. I'm not exactly sure what it is. But then when I add them together and I get, a third value, I'm going to get 0 divided by that number, whatever it is. And I'm just going to get 0. So we end up with a probability that this message is spam is 0. And that's not really the case, right? Because it does contain some other words that appear in spam messages. It just happens to contain a word that never appears or hasn't appeared in our corpus of messages. So what do we do about that? So this is conceptually how a Bayesian spam filter works. But in practice, in order to get around this problem of zeros appearing in the calculations, they use a technique called Laplace smoothing. The way that works is really simple. Anytime you've got a value to put into the table, you just add a really small positive constant to it. So rather than putting a 0 in the table, you might put in a 0.0001. Do the same thing for all the other numbers. Add on a 0.0001. And that will ensure that none of the values you put into the table are 0. They're always going to be at least that small constant. And then when you run your calculations, you just factor that constant out. And so that eliminates the problem of there being zeros. It just says that if a word appears that has never been seen before, it's assumed that it has a very, very low probability, not a 0 probability of occurring. So ultimately, Bayesian spam filtering is just one possible tool in the tool belt for a general purpose spam filter. It doesn't look just at Bayesian statistics. It also looks at things like, is the sender that the email message came from, is that a known spammer? Has that email message been, or email address been seen before as someone who's known to be a spammer? Or is there a file attached to the email? Sometimes that's a giveaway. Again, it's not a 100% dead giveaway that it's a spam message, but it's just one of many factors that you might take into account when determining if a message is spam or not. Does the message contain only just a link, just a URL for someone to click on? Or is that URL just one of just a few things in the message? That could be a giveaway. Or does the message contain a transparent 1-by-1 pixel image? It's called a tracking beacon. The purpose there is that when you open up your email message to be viewed, that 1-by-1 pixel image is not actually in the email message. It's off in a web server somewhere. So your email program, whatever you use, whether you use Gmail or you use the email application on your phone, has to go out to that web server and fetch that image to be displayed. Now, it's a transparent image. You're never going to see it, but that image has a unique file name just for you. So when you go out and fetch that image and bring it back onto the screen to be displayed, the web server now records what image was fetched by its unique file name. And therefore, the spammer is able to figure out who loaded that image. And that means most likely a human opened up that email message and read it. So now they know that you are more likely to open up spam messages because you loaded that message into the window. That's why on many email programs these days, loading images by default is turned off. So you have to click on something to get it to load the images. Or a lot of email programs also have been programmed not to load in these small little images, right? If you go and the problem is that you don't know if the image is going to be small unless you actually load it in. You actually go and fetch it. So I've heard about some email services, what they will do is rather than having your email program load that image directly, the email service will load that image for you, analyze it to see if it contains that tracking information, and if it does, it won't send it along to you. So when your email program goes and requests that image, it actually requests it from your email provider. Your provider loads that image, looks at it. Is this a 1-by-1 pixel transparent image? If it is, throw it away. If it isn't, then send it on to your client to be actually displayed. And then finally also the question was, does every new email also update the probabilities? And the answer is yes. So anytime a message is delivered to someone's inbox, it's assumed to be ham, and that updates the probabilities. And if something goes into the spam box, that also updates the probabilities. But more importantly, when somebody, the human reader, goes through and manually moves a message from one to the other. So if you go into your inbox and you see a message as spam and you hit that button that says this message is actually spam, it sends that information back to the spam filter and it updates its probabilities. Or if you go into your junk mailbox and move a message back to your inbox, that also updates the probabilities. And so here's where having a huge customer base can actually benefit you, because now you've got thousands of people who are essentially manually marking whether messages are spam or not. So it's kind of like the first person who receives a message and marks that as a spam updates the probabilities in the filter, and that benefits everyone else who's also a customer, who then opens up that message subsequently. Because now the spam filter knows it doesn't actually belong in your inbox, it now belongs in the spam box and actually doesn't show you that message at all. So a lot of spammers, what they'll do is they'll send out, let's say, 1,000 identical messages. That's also one key thing is, has the message been seen before? But let's say the spam filter doesn't know whether that's spam or ham, and it miscategorizes those messages as being ham. So those messages go into the inbox. Well, now people start marking that as actually being spam, and it can go through and find those messages and move them into your spam box so that you never see them. Okay, so that's pretty much what I had for you today. Let's take a little break. It's 11 o'clock, so we do need to take a little break. Let's take a little break, and then when we come back, I will show you the assignment for my students to do this week. It's basically more of these probability questions. And then there's no actual programming assignment this week. There's just these probability problems to work out. So let's take a quick break, not too long, maybe 5 minutes or so, and then we'll come back and we'll go over those problems.
Recording stopped.
All right, I don't know what, this thing keeps falling out of my ear. It's kind of annoying. What happened? Oh, did it become unclipped? No, it's still clipped back there. Didn't think I had to get my computer out today, but I guess I do in order to show this assignment to you. Now, your question is, discrete structure something you use in daily life? I would say, yes, of course you use this stuff in daily life. It's just that a lot of this stuff is hidden from you, right? So you use spam filters every day, you depend upon them, but you don't actually really program them yourself. And the previous topics we covered, like hashing cryptography, you use that every day. Probably use it hundreds of times a day. But again, you don't actually program them yourselves. You don't really interact with it directly. But it's good to know how that stuff works. What else? What else did we do? You know, things like Boolean logic, gates and circuits. Again, you don't necessarily use those you do use them every day, you just don't interact with them directly. So a lot of the stuff we cover in this course are all that stuff that's been hidden away from you, but form the foundations for modern computer science, modern programming. And I think if you want to be a good programmer and a good computer scientist, you need to know this stuff, or at least be aware of it. Even if you never write your own cryptography routines, at least you just have some idea about how they work. Because being able to know how they work can, well, I guess not only help you be a better programmer, so you understand some of the implications and some of the decisions being made, but also if you ever find yourself in a career in cybersecurity, you've got some idea about how your attackers are going to be trying to get into your systems.
Recording in progress.
Okay, let's go over the assignment for this week. So this assignment is in the form of a quiz, but it's really just some problems to work out. The computer is able to automatically grade your quiz. So the goal is to get like 100% on it if you can. If you do so, you'll get a complete on the assignment. You can take this as many times as you want. Let's see, there's a total of 8 questions on here. The questions have been somewhat randomized, and the values you see in the questions have also been randomized. So be aware that if you do the quiz again or the assignment again, you're going to get some different numbers. So let's just quickly go over these questions. If the probability of outcome A happening is 0.58, what's the probability that A didn't happen? Enter your number here. I would say use at least 2 to 3 decimal places for each one of your answers. Question number 2. One of those home cleaning robots, for example, a Roomba, that drives around your room cleaning up as it goes. It randomly goes forward, it turns left, turns right, or goes backwards. So if we know the probability that it goes forward is 0.57, and the probability that it turns left or right is 0.11 each, what's the probability that it goes backwards? Question number 3. A bucket contains 10 balls numbered 1 through 10. You take 2 balls out at the same time with no replacement. What's the probability that at least one of them has an odd number on it? Answer with at least 3 decimal places. Question number 4. If the probability of A given B is 0.12, what's the probability of not A given B? Question number 5. If the probability of X given Y is 0.74, then the probability of not X given not Y is 0.26. Is that true or false? Question number 6. Here are some three probabilities given to you. What is the probability of A given B? Answer using at least 2 decimal places. Probability of having a certain illness, L, is 0.22. There's a test for that illness. The outcome of the test is either positive or negative. We know the following probabilities about the test. The probability of a positive test result given that you have the illness is 0.74, and the probability of a negative test result given you don't have the illness is 0.84. If you run the test twice, you have the following Bayes network, in which the following variable L is connected to 2 variables, T1 and T2, with both of those being independent of each other. What's the probability of having the illness if the outcomes of both the tests are positive? Please answer with at least 2 decimal places. Okay, so I'm trying to put here, there's the whole question on the screen. And then last question, you have the following Bayes network in which the variable A is connected to x1, x2, and n3, and these x's are independent of each other. We know the following probabilities. What's the probability of A happening given that X happened, and X didn't happen? Please answer with the 2 decimal places. So that's it. Those are just the 8 questions there. Go ahead and submit your answers, and then when you see your answers, you'll be given the opportunity to watch some videos that explain how those questions were solved. So if you did get one of them correct, or if you didn't get any of them correct, let me say that again. If there's at least some questions you didn't get correct, you can watch the videos. I explain how to solve that problem, and you can go back and do the assignment again, and then use what you learned to be able to try again, and then shoot for that 100% on the questions. Once you get all the questions correct, you'll be marked complete for this assignment, and then that'll be it. That's it for this week. All right. So I think that's pretty much it. Let me look over here. I guess I have one more thing to bring up that's just, it's kind of interesting, and it's kind of relevant to what's going on these days. And it's a little bit less relevant than it was a couple of years ago when I first started working this out. See, when the pandemic hit and all of us were, sent into our homes, a lot of people wondered, have I had this coronavirus already? Like, there was a lot of people who kind of reported that in December of 2019, they didn't feel that well that month for maybe a week or so, but they couldn't really explain it. That actually happened to me in, I think it was December or January, somewhere in there. I just went through like a week where I just didn't feel very good. It wasn't really serious. It was just kind of like just being tired for that week. And so I wondered, have I already had the virus? Did I have it and didn't know it? Because they were saying at the time that roughly half of the people that catch the coronavirus will just never show any symptoms, or will show symptoms that are so minor that they won't even think they're sick. And at the time, this was before we had things like the at-home tests, right? Those didn't exist. And what I'm talking about is, these quick 15-minute tests that you can now get just at the store. Also didn't have what are called the Pcr tests, which are the ones that are currently used to determine whether or not you currently are infected with the virus. So this one here, is a very quick test, but the more accurate one is the one you can get like your doctor's office. The results take usually a day or two to come back. So at the time, back in February, March of 2020, there were some tests that came out which were called, what were they called? Antibody tests. And the purpose of those tests was to just see whether you had the antibodies to the coronavirus in your system, which would tell you, if it came back positive, which would tell you you have had the coronavirus infection in the past at some point. Your body has built up the immunity to it, and so this test would then determine whether you had the antibodies to that. And so a handful of those tests, maybe about a dozen or so, were very quickly approved by the government to be administered by like walk-in clinics or doctor's offices, or in some cases you could get these at the store, although they were kind of expensive. I recall them being about $200 to have one of these tests done. But here in the United States, the Food and Drug Administration made the statistics about these tests available, and anyone could go and look at them because it's a public organization, a public entity, and so they make these statistics available. Let me see if I can find those. So FDA emergency use authorization for antibody tests. I think this is it here. Yeah. So when your body produces antibodies, there's actually two kinds that it produces. One called IgGs and another one, I've just got to scroll down here, another one called, I think they're called IgAs. Oh, IgMs. And I did some research on this back then. I've forgotten a little bit of it. Basically, one of those antibodies is produced when your body is actively fighting off an infection. So it's kind of like a short-term, powerful antibody. And then one of them is produced as a long-term antibody, so that if you become infected again at some point in a later date, your body will remember what it got infected by, and then will start producing the cells in order to attack the invaders. So these antibody tests determine whether you have one of these types or the other, or even both of them. So you're looking through this list here, and you also see terms like sensitivity and specificity. So sensitivity is what we called, when we were working out these problems, what we called what's the probability of a positive test given that you have, in this case, the antibodies. And specificity is the opposite. What's the probability of a negative outcome given that you don't have the antibodies? So the sensitivity is called a true positive, and the specificity is called a true negative. So you don't have the antibodies, and the test result comes back true or negative. And sensitivity is you do have the antibodies, and so the test comes back positive. So you can scroll through this list, and you can see, now this list is much, much bigger than it was 2 years ago. when I looked at this list 2 years ago, there were only about 12 or so companies listed here. Now there's just probably hundreds. But you can see that, let's just scroll down here. You can see that, things like the sensitivity and the specificity can vary. Most of them are in the high 90s, but some of them can be lower than that. And also the thing you had to look at was what was their sample size. Like for this one here, it was tested on a total of 95 patients for which there was known to be antibodies in them. Like they actually got a blood sample and then looked at it through the microscope and said, oh, there are the antibodies right there. So we know that 95 of these people actually did have the IgG antibodies, and this test was able to successfully detect them 92 out of 95 times. So about a 96.8% success rate on that. And then there were 1,400 people that we knew didn't have the antibodies, and the test is able, this particular one is able to correctly identify that they don't have them 99.6% of the time. So, 2 years ago I was looking through this list, scrolling through it, and some of these sample sizes are pretty small, right? Only 30 people in this one and only 80 people in this one. It's not now 2 years ago there just weren't a huge number of people that had the coronavirus, and so the sample sizes by necessity had to be pretty small. But some of those sample sizes were really small, like only 10 or 15 people. These ones here, this is a pretty good size. What am I looking for here? Here, this one was actually pretty good. So this Biocan was actually one of the companies that came out with one of these tests very early on. And we got this table here of the performance. Now you can see these sample sizes are pretty small, but again, 2 years ago, there weren't just a whole lot of people that you could pick from at all. So by necessity, like I said, these sample sizes had to be pretty small. But you can see these percentages are still in the 90s, right? So you can be pretty confident that these tests are working well. So let's plug some of these numbers in and let's see how well they actually work. So recall that sensitivity means, you had the disease in the past, so you have the antibodies, and so this comes up positive. And specificity means you didn't have the disease in the past, and so the test is coming up negative. And so for the Biocan diagnostics, we've got the probability of a positive test given that you had the coronavirus in the past is 0.933, and we can see that right here. And the probability that you, the specificity was 0.962, and we can see that right here. And then I worked out the other numbers over here. Now what we didn't know at the time was these numbers. And so these are kind of like just assumptions. 2 years ago, we had no idea what those numbers were. And so I just assumed that maybe 5% of the population had had the coronavirus in the past, and therefore about 95% of the population didn't have it. Nowadays, of course, these percentages are much different, right? It's probably, given the latest variant that's been going through, this number here is probably more like, 0.6, 0.7, so about 70% of the population has now had the coronavirus. So again, these numbers are much bigger, but let's say this was, a year ago or 2 years ago, where the numbers were pretty low. So what we want to know is, what's the probability that you had the coronavirus given this test comes up positive? So you go into one of these testing laboratories, they give you one of these antibody tests, and it comes back positive. What's the probability that you have actually had the coronavirus in the past? Now the answer is not 93%. Let's figure out what it actually is. So let's use the table. we've been studying how to use the table. So we've got our prior column here, and this is coronavirus or not coronavirus. And we've got a positive test, P prime and P. Okay, so the prior for having had the coronavirus is, let's say, 5%. So it's 0.95 for not having it. Positive given coronavirus is 0.933. And positive given that you didn't have it is 0.038. So that's this number and this number. Okay, so let's multiply these across. 0.05 times 0.933 is a 0.04665. And then 0.95 times 0.038 is 0.0361. And then we'll add those together. And we get 0.08275. Okay, so far so good. Now we'll come up with the actual probability, which is 0.04665 divided by 0.08275. And we come up with 0.564. Okay, so when I worked out these numbers myself, I was actually kind of surprised by those. What does this number tell us? It tells us that if we took one of these antibody tests, there was about a 56% chance that we actually had the coronavirus in the past. Now, to put that in perspective, that's about what a coin flip is, right? So there, you flip a coin and there's about a 50% chance that it comes up either heads or tails. So you take one of these tests, it comes back positive, and there's only about a 50% chance that you actually have had the coronavirus in the past. Now, this test would have cost you at the time about $200. And I'll tell you, you could save yourself $199.99 if you just flipped a penny, right? You flip a penny, it comes up heads, and you go, oh, I had the coronavirus in the past. I just saved myself almost $200, right? These tests, even though they look like they are, nice and sensitive, nice and accurate, these numbers don't tell the true probabilities because it depends upon whether or not you've actually had the coronavirus in the past. Right? So basically, even though this one appears to be 93% accurate, it really is only 50% accurate at telling you whether or not you've had the coronavirus. And that's all based upon the fact that we're assuming that only 5% of the population actually had the coronavirus. And in fact, down here, this did not exist 2 years ago. There's now a table down here that shows you what the actual percentages are given the prevalence assumption. So if we assume that 5% of the population has had the coronavirus, this test is actually only about 50% accurate. However, as the numbers go up, so as more and more of the population has had it in the past, then of course this number goes up as well. So maybe this is more like where we are today, but 2 years ago, this is where we were. And so, I asked myself, should I actually go and get one of these tests? And then I worked out these numbers and went, no, I shouldn't go get one of these tests. It's not going to tell me anything, really. Turns out later on, I actually did have one of these tests, but it was ordered by my doctor, so I got it for free. And I didn't have the antibodies. So what did that mean? That means I can't explain why I was really tired for that couple of weeks back in January or February of 2020. Who knows what happened then? I don't know what happened. I was just really tired. I don't know about you, but that happened to me several times during the first year or so of the pandemic. You know, we were all at home, not exposed to other people, and there were just some days when I just felt exhausted. I mean, just like I just wanted to sleep, and I couldn't explain it otherwise, other than just maybe something is going through my body and is making me feel just really tired. But you know, I would sleep the next day, and then I would sleep that night, and the next day I'd be fine. Um, you know, I asked some people, and they said they were having that too. It's just like just a couple of days where you just feel really tired. Can't explain it. My hypothesis at the time was that I was actually like catching maybe a cold or something like that. But because my body, because we weren't exposing ourselves to each other, like, you know, all that winter and all that summer, our bodies basically were just like revved to go. It's just like, you know, we've got, our immune system has nothing else to do. And so as soon as like some virus comes in, it's just the common cold, it just battles it off immediately, right? Just boom, it's out of there. And so my body is basically fighting off cold really rapidly. Whereas what would happen in the past was, you know, it was so busy fighting off some cold, let's say 1 week, that you would catch another cold the next week, and it just didn't have time to recover. So that was my hypothesis as to what was going on, was that my body was basically fighting off infections as fast as it possibly could. I went through a whole, almost a year and a half where I just never caught a cold. It was great, right? Did that happen to you? You just went through a whole year or so where you just didn't catch anything at all? No flu, no colds, no nothing. Yeah, Sergey's writing here, because that happened to him last year. Your body was just overreacting to any cold that came in. Oh, it's terrible. Your tonsils would swell up, you'd get a fever, right? You're not feeling good, you don't want to eat. And then what, the next day, 2 days later, you're fine. Oh, man, that's terrible. You're saying your tonsils will swell up and just make your throat just really constricted. Ugh, sorry about that. But wasn't that great? Like for a whole year, we didn't catch the flu, didn't really catch any colds. And it's almost like the masking worked, right? Now whenever I go to the store, I'm like, I see someone sneezing. You know, we're all like conditioned now. Whenever we hear someone coughing or sneezing, we like back off, like, you know, what have you got? I don't want to be near you. Does that happen to you? Like you're just hypersensitive now to coughing and sneezing than anyone does. Hey doggo. My doggo decided to join me. Hey, you want to come up here? He's just a medium-sized dog. Come on. Oh, see if I can pick you. You are turning into a fat dog, but here we go. Here's my dog. This is the guy who hangs out by my feet. Oh. His name is Shakespeare. All right. You gonna hang out here? Keep my feet warm? Oh, he's hungry. Oh yeah, he's kind of fluffy now because I need to give him a shave. I just haven't done that yet. He doesn't like that at all. Oh, see you later. Bye. Hang on, I gotta close the door. And then usually I have a cat hanging out here as well, but I think I don't see them right now. Usually they're stuck in some corner or in their closet or something, but no cats at the moment. They're out, probably hanging around by the food dish waiting for me to feed them. Okay, well, I think we've come to the end of it. Any last questions? So next week, let's see, very quickly. So next week we've got a class on Monday and Wednesday for the discrete structures. And we're going to be doing, I think we're getting into graphs next week. Let me quickly look here at the list here. So graphs, and we're going to be learning about graph algorithms. Let's see, let me scroll through my list here. I've lost my place. Come on. Yes, so we're doing graphs. We'll be learning about the different kinds of graphs and then graph algorithms such as shortest path, spanning tree. Well, those are the two primary ones that we need to cover, shortest path and spanning tree, plus depth first search and breadth first search. And then we will get into finite state machines, which are a special kind of graph, but can be used to do things like pattern recognition. And so that'll lead into a discussion of how things like programming languages and compilers work. Again, you use them if you're a programmer every day, but you may not have thought about how does a compiler go about turning your code that you wrote, let's say in Java or in C, and turn that into the actual assembly language instructions in the machine code that gets executed by the processor. So that'll be the whole rest of the semester. Now we, here in the United States, we have 1 week off starting April 11th. I think that's the date, April 11th, thereabouts. And that is our week of spring break right before Easter. And so there will be no live streams during that week. So we're going to be here next week to start talking about graphs. We'll take a week off. We'll come back the week after that to finish up talking about graphs, and then we'll get into finite state machines. And that'll be most of the rest of the semester. That'll be about 2 weeks or so, I think, for finite state machines. And that leaves about a week and a half where I kind of like have nothing really scheduled. And that's where we could just talk about some other topics of interest. Things like quantum computing, I know a little bit about, and I can teach you a little bit about that. Or we'll see what we come up with, right? So quantum computing is one possibility. Maybe making a very simple compiler, like actually programming writing a program to actually translate a simple programming language into some assembly language instructions. We could do that as well. So there's a whole bunch of stuff that we could do during that week or week and a half where I have nothing scheduled. Okay, so I think that is it for today. Thank you for joining me, and I will see all of you next week. So first I'll say goodbye to my Zoom folks, and then I'll say goodbye to the YouTube folks. So bye-bye Zoom folks. Have a great weekend, and see you on Monday. Take care. Bye-bye. And then YouTube folks. Oh, Nunya, you said you've not been sick with a cold since 2009. That is amazing. And I've only been sick just a handful of times since 2020. Although now that the kids are back in school and we're back out shopping again, I've gotten like sick more times in the last 4 months than in the whole previous, 2 years. So this is the part of returning to normal life that I've been not looking forward to, is now just catching colds again. But good thing is now the FDA has just approved boosters for people over the age of 50, which is me. So as soon as those become available, I'm going to go tootle out there and get myself another booster. I mean, why not? All right. Hey, thanks for joining this stream. And again, we'll be back on Monday, and we'll be talking about graphs. Or you can join me on Thursday, that's tomorrow. And we're going to be still talking about writing programs to crack password hashes in C. So we did some of that stuff a couple of weeks ago. We did it in Python, and I also showed you Hashcat, which was a program that can do it really, really fast using a GPU. But in this class, we're using the C programming language in order to crack hashes a little bit slower, actually a lot slower than a GPU does, but it's a lot higher performance than the Python programs that we wrote. And we're going to be using dictionaries that are much bigger. In the Python programs, we use a dictionary that I think I had 200 or 300 words in it. And with the C program, we're going to be working our way up to a dictionary that has 3 million entries in it. And it's going to be great to see those programs really fly through all of those hashes and crack them quickly. Oh yeah, they haven't said anything about whether the boosters have been updated for the latest variants. As far as I know, it's still the same old boosters we've gotten, or the same old shots we've gotten for the past year. Just number 4, right? We had 2 shots, and then a booster, and then this is number 4. And so what'll happen is I'll get it, and then the next day I'll feel kind of awful. Not really awful, I'll just feel tired. And then that'll be it. It'll be good for the next 6 months or so. Okay. Well, again, have a great weekend, and I will see you all either tomorrow or next week. Have a great weekend, everyone. Stay safe, stay well. Talk to you later. Bye-bye.